Okay, thank you for the introduction and thank you for having me to do the presentation and share my work today. My name is Chen. Today my topic is selective electrocatalytic reduction of nitrate to nitrogen and alkali recovery over functionalized palladium and copper electrode. Okay, and this is my outline for today. And so first I will give you a small introduction and then objective and material and method, results and discussion. And last one is gonna be a conclusion. And then so this is a general property of the nitrate. And then so the most commonly seen of nitrate is hydrogen nitrate, and then sodium nitrate, ammonium nitrate, and potassium nitrate. And then the all of them has a high solubility, okay. And then so they are stable under ambient condition. Okay, and then so the source of the nitrate can be divided into two parts. So first is from the natural source. For example, nitrate can be generated from the nitrogen strike, and also it can be generated from the bacteria utilize oxygen to convert nitride into a nitrate in the soil. And then so for anthropogenic source, so it can be generated from the agricultural activity and also industrial process and the domestic waste. Okay, so here is application of the nitrate. So it can be used as a fertilizer because it has nitrogen, and so nitrogen is the source for plant to grow. And also it can be used as explosive because, for example, the ammonium nitrate is highly oxidant, so it can be used as the ingredient to make explosive. And also for medical part, nitrate can improve blood flow. And also for food addictive, it can be used as a preservative, and also it can keep the food to stay longer. And also it has the function of color fixed active. And for the industrial uses, it can be used as a corrosion inhibitor. So the effects of the nitrate for environment and human health. So for environment health, nitrate will lead to excessive algae and microorganism growth, especially cause eutrophication. So as you can see from the picture, when sometimes the reservoir or the lake, the surface turning green. So this is kind of the phenomena of eutrophication. And then for human health, especially for the newborn baby, if the newborn baby, they intake the drinking water contain nitrate higher than 50 milligram per liter of the concentration, so it will lead to blue baby syndrome. So it means the skin of the baby will turn blue. Okay, so this is current regulatory status for the nitrate. So for drinking water, the nitrate, the limit is gonna be 10 milligram per liter. For nitride, it's about 0.1 milligram per liter. For industrial effluent standard, the limit is gonna be 50 milligram per liter for nitrate and 10 milligram per liter for ammonium. Okay, and then so this is the hypothesis of this research. So bimethodic catalyst could have the higher nitrate reduction efficiency than mono methodic catalysis, and electrode deposition process could enhance the nitrate removal. Okay, and then so the objective is we try to fabricate, categorize, and improve catalytic electrode for the nitrate reduction. And also we would like to evaluate the integrate electrocatalytic and electrodialytic system for alkaline recovery simultaneously. Okay, and then so this is how we prepare our catalytic electrode. So actually, we are using electrode deposition process. So first, we will prepare a palladium solution And then we use graphite as an anode, copper mesh as a cathode. And then so when we apply potential, so the palladium will be deposited onto the copper mesh. And then so during this electrode preparation, we will change the deposition time for the palladium. The time is range from 60 seconds to 360 seconds. We want to know if the loading of the palladium will affect the nitride removal or not. Okay, and then so this is the reactor we are using. So we call it the integrated electrolyzer and the electrodialysis system. So as you can see from the reactor, so we use two cation exchange membrane, try to divide it into 3 chambers. So the in the middle part is the chambers where we have our catalytic electrode. And then so this is the place where we try to reduce the nitrate to nitrogen. And then so the third chamber is gonna be the chamber where we recover the alkaline. Okay, so in this reactor, we are trying to do the nitrate reduction and also recover the alkaline at the same time. Okay. Okay, and then so here comes a result and discussion. And this is the image of electro categorization. So the image A is the copper mesh. And then so start from image B to image F, we started to deposit a different amount of palladium with different times, start from 60 seconds to 360 seconds. And then so it can be seen from the figure C, we started to see some dendrite morphology on the electrode surface. Okay, and also with increases with deposition time, we see the roughness on the electrode. Okay, and then so this is the SPS spectrum of palladium and copper electrode. And then so the image A and the C is the spectrum of the palladium, and image B and D is the spectrum of the copper. And then so the image in the lower side is the image is a spectrum before nitrate reduction. And then so image on the top is the spectrum after the nitrate reduction. Okay, so as can be seen, the spectrum shift to lower binding energy due to the charge transfer. And then so the copper two in the palladium and copper electrode indicate lead copper oxidize to carbon oxide. And also the copper 2 peak is getting broader, indicate the copper 0 is oxidized to copper oxide. And during the reaction process, by carbon 0 gain electron, so that the nitrate is able to be reduced to nitride. And this is the CV test of the palladium and copper electrode. The scan rate is 20 millivolt per second, and then so we have platinum as the counter electrode. Okay, and then so the pH is 3, and so as can be seen with the increases with nitrate concentration, so we are observing the peak is getting larger and wider, and then so this shows the nitrate reduction peak on the surface of palladium and copper electrode. And then so this is the nitrate reduction on different electrodes. Okay, so the S-axis is the different materials. So first one is stainless steel, and then the second one is copper, and then the third one is we deposit copper on stainless steel mesh. And then this is palladium. We deposit palladium on the stainless steel mesh, and the last one is that we deposit palladium on the copper mesh. Okay, and then the experiment condition is we have about 10 millimole of nitrate, and then so pH is 3, and then so as can be seen, the copper shows the ability of nitrate removal, and with with the palladium, the PD shows the selectivity to nitrogen. So I will show you the mass balances of the data in the following slides. Okay, and then based on this experiment, the PD palladium and copper electrode was chosen for the following experiment. And then this is effects of pH on nitrate reduction. So in this experiment, we try to do from pH 3 to pH 7 in this pH range. The y-axis is the nitrate removal and the nitrogen selectivity. And then so based on this experiment data, the palladium and copper electrode can remove nitrate at different pH ranges. Okay, and then so the lower pH shows the reduction, can reduce the formation of the nitride. And then so with pH increase, the pH surface covered with hydroxide ions, so it might be limited the nitrate to get access to the electrode. So this is the reason in the higher pH maybe nitrate is not easy to be converted to the nitrogen. And then so at the pH 3 was chosen because based on this experiment, it shows the higher nitrate removal and also nitrogen selectivity. So pH 3 is gonna be the parameter for the following experiment. Okay, and then so here is shows the effects of palladium loading on nitrate reductions. Okay, so in this experiment, we try to deposit different palladium, different amount of the palladium by using the changes of deposition time. Okay, and then so as can be seen, the different palladium loading on copper affect nitrate removal and nitrogen selectivity. And then so with increases with palladium loading, especially when we deposit palladium more than 240 seconds, it will lead to a decrease of nitrate conversion. This could be the less activate side of the copper, because this might be the space of the copper is covered by the palladium. Okay, so it also shows if we want to reduce the nitrate, we also need to have a certain amount of the copper. Okay, and then so based on this experiment, the highest nitrate reduction is palladium deposit with 180 seconds, so which is about 0.44 weight percentage. Okay. Okay, and then so this is the data we use the nitrogen reduction and alkali recovery use the electrolyzer and electrodialysis system. Okay, and then so here, as you can see from the image on the left, okay, and then so this is the mass balances we have done, and then so around after like 6 hours, we have almost about almost 100% of nitrate removal. And then also we have more than 90% of the nitrogen conversion. And also with assist of the palladium, we can keep the nitrate and the ammonium concentration in a very low content. Okay, and then so this is the function of the palladium. Okay, and then so the image on the right is the alkali concentration on the third chamber of our reactor. So in here, it shows we are able to recover about 350 millimole of the OH concentration. Okay. Okay, and then this is the summary. The palladium deposit on the surface favor nitrate reduction and nitrogen selectivity. Also, palladium loading affect the nitrate reduction, especially for the palladium deposit for 180 seconds, shows about 98% of nitrate reduction and 91% of nitrogen selectivity. And also, we integrate electrolyte with electrodialysis, shows the nitrate reduction and alkali recovery are feasible. Okay, and finally, I would like to thank the National Science and Technology Council for the financial support, and also the group members of my research members. Thanks for their effort on the research work. Thank you very much.
Thank you very much for your nice talk. If there is any question for, yes.
Hello, thanks for a wonderful talk. I'm just curious about, I have two questions. First one, when you show the effect of pH, we saw the selectivity decrease with increasing pH. So is it safe to say that because in alkaline environment, which convert to the standard hydrogen potential, it's higher. So is it safe to say that when you want to do the reduction, when you apply higher voltage, the selectivity will drop? This is first one. And the second one, when you in the last two slides, you show the OH minus concentration of OH minus is 1 millimolar. But just it's a stupid question, but when you apply 1 millimolar OH minus, the pH shouldn't be like 11, 10 or something, but in your case, you just show pH is 9. What's 9? pH 9. Thank you.
Okay, thank you for your questions. So first question is about the pH effect. Okay, so actually when you increase the current or voltage for the natural reduction, actually it is possible to have the overreaction to produce the ammonium. So actually there's one of the data we didn't show. We also try with a different current density, and then so actually we have optimal or the current density for this experiment. So when we have